Hi everyone, my name is Elsa Tang, and I'll be talking about CO-to-H2 conversion factor in nearby galaxy centers, which is a joint work with my advisor, Karen Sandstrom, and the FANS collaboration. So our motivation is, of course, to study the CO conversion factor, or alpha CO. And we know it is a critical factor to tracing molecular gas in galaxies because the low J CO lines has been the most commonly used tracers for tracing the bulk molecular gas. And so the factor has direct impacts on many of the star formation properties as long as it is inferred from molecular gas mass. However, alpha CO is known to vary within and between galaxies, and it should depend on various gas properties. So for example, the upper figure shows that alpha CO can vary up to orders of magnitudes in different environments. And also you can see that for more extreme environments, like in Euler's, they usually have lower conversion factor than the standard Milky Way value, which is probably because of higher temperature or turbulence that could increase CO emission and then decrease alpha CO. And even more interesting, from the figure below, you can see that recent studies also found lower alpha CO in the centers of relatively normal star-forming galaxies. And so it is possible that activities in galaxy centers like nuclear starbursts or gas inflows can also lead to extreme CO excitation or dynamics that could alter the alpha CO value. So the goal of our work is to understand how and what specific gas conditions are varying the alpha CO in galaxy centers. So to do this, we first select 3 nearby barred galaxies that were already found by previous studies to have lower alpha CO in the central kiloparsec regions. And then we use ALMA to observe multiple 12 CO, 13 CO, and C18O lines toward the central 2 kiloparsec regions of these galaxies. So it's labeled by the yellow box on these images. And we will match the beam size of all 6 lines to around 100 parsec, which corresponds to the giant molecular cloud scales. And then we use non-LT radiative transfer code to model the intensities of all 6 lines and to study the likelihood distributions of various physical parameters, including CO column density per line width, temperature, densities, abundances, and beam filling factor. And then with these directly modeled parameters, we can further constrain the alpha CO likelihoods in each pixel. So here from this plot, you can see how our modeled alpha CO solutions vary with the galactocentric radius. And it's clear that the alpha CO in these galaxy centers are systematically lower than the standard Milky Way value. And in some places, it can even reach like 15 to 20 times lower, for example, like in the inflow regions of NGC 3351. So now to connect the derived alpha CO values with gas properties, we found that there's a strong correlation between alpha CO and the CO optical depth in optically thick regions, which is most of the pixels in our galaxy centers. And this correlation can explain most of the alpha CO variations we see in these 3 galaxy centers. But also you can see from the figure below that alpha CO also decrease with our modeled kinetic temperature, which makes sense because higher temperature would also increase CO emission and decrease alpha CO. But here in the temperature relation, we find that the scatter is about 4 times larger than the relation with optical depth. So it's clear that the dominant driver of alpha CO is the CO optical depth than the temperature. So now knowing this, the next step is to think what we could do to trace these alpha CO variations. For example, if we can identify observational tracers for alpha CO. So in our earlier paper published last year, we already showed that the substantially lower alpha CO we see in the inflow arms of NGC 3351 is mostly because of the increasing CO emission due to very low CO optical depth. And this can explain why we are observing increasing CO to 13 CO line ratio and the CO line width in these inflow regions. And now in our current work, we further extend this by including all 3 galaxy centers. And we can see that there are indeed clear trends of alpha CO decreasing with the CO to 13 CO line ratio and the CO line width. So to conclude, we think that both CO to 13 CO line ratio and CO line width can be good observational tracers for alpha CO because of their relation with the CO optical depth. And this should be especially important in galaxy centers or similar environments because there we would expect the CO optical depth to be generally higher and spans a wider dynamic range. So I'll end my talk here, but if you are interested in more details or results, I'm happy to chat. Thank you very much.
Hi, great talk. I was interested, so I've been doing some of the non-LTE modeling myself, and I was curious what you did for abundance ratios between the various isotopologues that went into that modeling.
You mean how we did the abundance ratio?
Or did you use an assumed abundance ratio?
No, abundance ratios are also our directly modeled parameters. So we have basically a 6-dimensional model grid. Yeah.
Cool.
So yeah, we didn't assume fixed abundance ratios.
Right. So you talked about this in terms of barred galaxies, but would this also extend to other systems that have optically fixed CO or higher temperatures, like mergers, for example?
Yeah, right. So there have also been many studies on LERGs and ULERGs, and they also found lower conversion factor in those regions. And yes, our modeling can definitely extend to those systems. Yeah, but I mean, like galaxy centers are like more interesting because in LERGs or mergers, we do expect that there is definitely more extreme environment. But like in normal star forming galaxy centers, maybe we don't expect the environment to be that extreme, but it turns out that in galaxy centers, there are indeed effects on alpha CO.
Might this apply to some of the high redshift starburst type galaxies that people have observed? Nearly qualitative data.
Yeah, I think for higher redshift galaxy, it may be more challenging to detect CO lines. So like most high redshift galaxies use other tracers, but I mean, if you have the ability to detect the CO lines, this should definitely be able to extend to those systems.
Thank you. Now from Laura Lemke.